All right, so here's the deal. These linear programming problems, they are a lot of steps. And if you just watch me in class and don't try it on your own because you think it's too scary or too difficult, which it's not, you just have to practice it like everything else in life. I saw all of you walk into my room just fine today. But guess what? When you were born, you couldn't do that. But you practiced, and now you're amazing at walking. Even Mitchell. So you just have to practice this stuff. And even if you're worried that you don't get it right, that's fine. That's how you learn. If you're doing a problem and then you do something wrong and mess it up, then once we recognize what that mistake is, you're going to remember that a lot better. You're like, oh, wait, last time I was doing this all the time and I forgot, and that's not what I'm supposed to do. That's what learning is. It's realizing what you did that wasn't right, that now you can fix it and you can change that action for next time. So these word problems here, which I do have posted on the calendar, if you need to pull these up, these word problems here, you've got to try them yourself. You've got to work through them for this linear programming process, all right? Now, here's the other part of this. Even though I'm calling this homework, I mean, the whole purpose of homework is for you to get the practice so that you feel more confident with this, so you can learn how to do these correctly before I assess you on it, before I measure, hey, did you learn this? If you don't try it, you're not going to learn it. With these ones, I'm not actually going to go around and look at every one of your notes and determine, hey, did you actually do all 6 steps correctly? So I'm not even going to check this, all right? I'm telling you flat out, I am not going to check this homework come Tuesday next week, all right? But this is up to you. Are you going to choose to learn from this, to actually give it an honest effort and try to learn? Because you will be tested on this eventually. And if you just take the weekend off, great, you got some free time. But then come test, how are you going to feel when you look at one of these word problems for real for the first time? You're like, oh, I don't remember how to do this. And then you're going to be like, Wojcik, is there a retake? Yeah, we know that's going to happen. No, you didn't. You didn't. All right, so here's what I want us to do. These 6 word problems are all already halfway done because these are the same word problems that we wrote constraints for on Tuesday a week ago, all right, a week and a half ago. You've already gone through these problems. You should have these already in your notebook with all the constraints already written, right? I'm hoping somewhere. We defined the variables, we wrote the constraints, and then we rewrote them in slope-intercept form so we could graph them right away. That was what we did on Tuesday last week. If you don't have this anymore, if you lost it, guess what? I've recorded that lesson and it's posted online. You can find it on the link to it on my calendar. You can go to YouTube and search up Wojcik Algebra, and you can find the video there too for 2.3a writing constraints. That's all on there. You can look that up. You should have it already. All right. So there should really be no excuse to not have that. What I want you to do now is the second half of linear programming. So we've got the constraints. You all have those already. You can at least look them up again. What you need to do now is take those constraints and graph them on a coordinate plane, right? Find that feasible region when you do all the shading, and then check out those critical points, all like the vertices, the corners of the feasible region. And you got to take each of those points and plug them into the z function. Now, the z function is also something that we didn't do last week, the optimization function. So even though I assigned this as homework that was due today, looks like most of you have not done that. Some have, but not everyone. So what I'm going to do is go through these 6 problems, and I'm going to give you a little boost. I'm going to go through right now and show you each, or we're going to come up together with the z functions for every one of these problems. So now your assignment that is due on Tuesday at the beginning of class is going to be to graph the constraints, right? Find that feasible region. So you're going to need to use some graph paper. You can take some from the back if you want. And then you're going to need to find all those corners, all the vertices of the feasible region, and plug them into that z function. Once you do that, the easy part is just you decide, are we trying to maximize or minimize something? And all you do is pick the biggest number or the smallest number, and then write that final answer. Like, we should make 10 pieces of plywood and 6 pieces of lumber for a maximum profit of $500, whatever it is, right? Write that conclusion sentence, okay? So you've got to go through those steps to get familiar with them so that you understand them, so that you learn them. Now, I can teach you how to do this. I've been teaching you this stuff for 2 weeks now, but it's up to you to learn it, right? You've got to take that next step. I can't force stuff into your brain. I can present it to you, but you got to work on it a little bit to make it stick in your brain. So let's go through these 6. We're going to write these constraints, or I'm sorry, we already had the constraints. We're going to write the Z functions. So this bran muffin and corn muffin one, we're going to just write the Z function together. Z equals, and this Z function is always going to have just 2 terms, one X term and one Y term. And the X and the Y are going to have some type of a coefficient, a number in front of them that's going to be based on whatever we're trying to optimize. And to figure out what we're trying to optimize, all we need to do is look for that word maximize or minimize. Typically, it's going to be in the last sentence somewhere or whatever the question is, right? And I look at the last sentence. It says we're trying to, there's the word maximize. Well, what are we trying to maximize at this bakery? We're trying to maximize profit, which is a very common thing. That's probably one of the most useful reasons for using linear programming. You're trying to make more money, right? That's what businesses are trying to do. So we're trying to maximize profit. That means my Z function needs to contain the profit for each of my 2 variables, which in this case are the bran muffins and the corn muffins. So can you see in this word problem somewhere where it talks about the profit for bran muffins? What's it say? How much? Yeah, right here, the profit for these bran muffins is $1.25. So we make $1.25 for every bran muffin, for every X that we sell. I think it's for a box, technically, of bran muffins. So we'd write that as just 1.25x, right? I get $1.25 times X, times every box of bran muffins that we sell. But that's not the only profit we get, because we also will add the profit that we make from those corn muffins. So what's the profit on a box of corn muffins? Yeah, 1.35. It says right here, profit for corn muffins is $1.35. So we would write 1.35y. And that's our Z function. So then your task for Tuesday is to then graph those constraints from last week. And you're going to just find that feasible region, take those coordinates, all the corners of that shaded region, and you're going to plug every one of those X and Y combos in for X and Y, each of those points. And then since we're trying to maximize, all you need to do is pick the biggest number when you plug in all those different critical points for X and Y. Who thinks they can do that? Yes, yes, yes. Confidence. I love it. We got this. All right, let's go through the others just to make sure that we understand what's going on. So I'm not going to read the whole thing. I'm just going to go to look for that optimization word. Again, typically it's in the last sentence. And sure enough, I see the word maximize right there. And what are we trying to maximize? The number of people processed. So remember, this was the airport that are buying the 2 different metal detectors, Unit A and Unit B. And they can process or basically like scan different numbers of people. And we want to be able to scan the most people per hour. We want to get the most people through the airport. We don't want them waiting around in security forever. And so our Z function is going to pertain to the number of people that each type of metal detector can process, right? There was the Unit A and the Unit B. So look in this word problem. Can you see where it says how many people the Unit A metal detector processes? It's like a Where's Waldo hunt, right? How many people can Unit A process? How much is it? 300. So right in the middle kind of, it says Unit A, it's got the cost, security guard, but it also says it can process 300 people every hour. So that's what I'm trying to optimize here. So that goes into my optimization function. All right, Z equals 300x, because that Unit A metal detector can process 300 people. Every one of them can process 300 people. So if I had 2 of them, I could do 600 people, right? Because it's 300 times 2 or so forth. Now, what about the unit B? How many people can unit B process? Yeah, it says it right in the next sentence. Unit B can process 500 people. So how would I write that in my Z function? That's it, plus 500y. That's all there is to it. Plus 500 people for every y, for every unit B metal detector. All right, so that's your Z function for number 2. All right, this is the 2 different calculators, a graphing calculator and a scientific calculator. And what are we trying to maximize in this problem? What's it say? All right, look for the word maximize or minimize, and it's right there. Trying to maximize profits. Again, it's a business, it's a company. They want to make more money. So we're going to maximize profits. Now, here's the tricky part to this one. Does it say the word profit anywhere else in this word problem? Does it say the profit on this calculator is this much? I see the selling price and the cost. Now, if you're not too familiar with finances, the way that you determine the profit that you can make is basically if I'm making something, I have to usually buy supplies, right? I have to pay my employees. I've got bills or whatever. So there's a certain cost that I, as the company owner, have to pay. So to make a calculator, there's a certain cost to that for me to make one. Once I've made it, I'm going to turn around and sell it for a higher dollar amount. And then whatever that difference is my profit, right? And so if I'm looking at the like the scientific calculator, the graphing calculator. So like this scientific calculator sells for $60. So I'm making these scientific calculators and I'm selling them for $60, but it costs $35 to make a scientific calculator. So I've got to buy all the parts to it. I've got to pay for the machines, right? The employees to put it together. So I'm going to pay $35 to make a scientific calculator, right? That comes out of my pocket. That's money that I lose. But then I'm going to turn around and sell that scientific calculator for $60, right? I sell it for more. And then my profit is the difference between those two numbers. It's how much that I actually make. So what is the profit on a scientific calculator here, everybody? 25, right? You take the selling number, the $60, and you subtract the cost to make it of $35, and that means you've made an additional $25. So we'd write this as 25x. So that's the profit for a scientific calculator, right? That's the additional money that I make. Because I didn't have to pay any of that. That's all money in my pocket. And now we have to do the same thing for the graphing calculators. And it says the graphing calculator, we're selling it for $105. Right? In the stores, it's gonna be selling for that much. But the cost of the graphing calculator is $75. So I've got to pay $75 to make a graphing calculator. But then I sell it for $105. So what's my profit on those graphing calculators? 30. Yep, 105 minus 75 is 30. So I make $30 for every Y for every graphing calculator. And that's my profit. So this one was a little bit tricky to figure out that Z function because you just had to do a little extra math. But again, all you're doing is subtraction, which I know you're all pretty good at subtraction, right? Yeah, we got it. All right, this is the truckloads problem. And you look in that last sentence. And this one's a little different because it says we're trying to minimize instead of maximize. So they're trying to minimize the cost. Remember, cost means what the company has to pay in order to operate. So that's like money that we're losing because I need to pay a certain amount, like I have to pay for the truck drivers or whatever. And so I need a Z function dealing with cost. And if you look at this table, you've got the cost right there listed for each type of truck. So this one's a pretty straightforward Z function. right? We're just going to say Z equals, and then the cost for a small truckload is right there. It's $70. So $70 for every X, $70 for every small truckload. And then for the large truckloads, it cost me $60, so plus 60Y. And that's this Z function. Now remember, when you finish this problem and you graph it and you test out all those points, and you plug those test points or those critical points into the Z function, this time we're trying to minimize the cost, so don't pick the highest number. We'd pick the smallest number in this case. So you might want to put like a star by this problem or something to remind you, hey, make sure that we realize we're minimizing in this case, right? Because the first three we're all maximizing. So in this case, just pick the smallest number instead of the biggest one, because we don't want to have a lot of costs. I don't want to have to pay a lot of money. I want to make a lot of money. All right, then we have the hospital that's trying to advertise through TV commercials and through newspaper ads. And the optimization piece, if you look down at the bottom, what are they trying to maximize? The audience exposure. Basically, they're trying to reach as many people. They want as many people as possible to see their ads that they're paying for. And so we want to maximize the number of people that see the newspaper ads or see the TV commercials. So we need to know, well, how many people do each of those get exposed to? And so it says that the TV commercials reach 14,000 people. So that's the audience exposure. So a single TV commercial is going to reach 14,000 people. So we'd write 14,000 X, 14,000 people for every TV commercial that we produce. What's up, man? Sure. Have fun.
Thank you.
You're welcome. All right, below it, you see the newspaper ads reach 6,000 people. Kind of makes sense, right? Not as many people read the newspaper these days. They're just going to watch TV. Plus 6,000 Y. We'll just watch it on YouTube. Did any of you watch the news ever? Yes? No? Maybe? All right, so then we want to maximize audience exposure. So I want to know what combination of the newspaper ads and the TV commercials should we produce in order to reach as many people as possible, given those other constraints. Last one. All right, Charlotte's working some summer jobs. And what are we trying to optimize here? We'll look down at the bottom. This is another minimize problem. What are we trying to minimize? Well, we're trying to minimize her coffee consumption. So she doesn't want to have to drink too much coffee. It makes her go crazy, but she needs it to stay awake. So then our Z function is going to be the coffee consumption for each of her two different jobs. And so let's see. Working at the movie theater causes her to drink an average of 6 ounces of coffee per hour. So that's at the movie theater. So we're going to write 6x, 6 ounces of coffee for every hour she works at the movie theater. Dog walking is apparently not that stressful because that only causes her to drink 2 ounces of coffee per hour. So then we're just going to add 2y. Then you plug in the number of hours of working each job. And you figure out how many total ounces of coffee it's going to take for her to stay sane during these two jobs. And that's it. Any questions for me on how we got any of those Z functions? Or are you feeling pretty good about writing those optimization functions? Can I get a quick thumbs up, thumbs down check? You're like, yeah, that made sense. I can get that. Okay. He had 2 thumbs up, right? Okay, so everybody, The expectation is that you complete these problems. You need to graph them. I gave you graph paper last week. If you still have that, you can use that. If not, I've got some sheets in the back you can borrow for linear programming. Then you got to shade that feasible region. Find those different corners in the feasible region. It could be 3, it could be 10, whatever the number is. You plug every one of those critical points into each of these z functions, right? And then you look for either the biggest number or the smallest number based on if you're trying to maximize or minimize something. Any more questions before we sign off? Anyone from home? All right, so cohort A students at home, the expectation is for the rest of the class, you are working on finishing these linear programming problems. All right, get that done right now. You've got over an hour. While cohort B, who's here with me, you're going to take your test. All right, everyone at home, you may sign off and feel free to email me or hit me up in the GoGuardian chat if you have any questions. Otherwise, have a super duper day.